Math 148, 13.2, the definite integral area under a curve. So to evaluate definite integrals using the fundamental theorem of calculus, to use definite integrals to find the area under a curve. Consider f of x be defined on a closed interval a to b. We can divide that interval into n subintervals, not necessarily equal, with n points in the interval. So x sub naught, i.e. the very initial one, is a. Then I have x1, x2, up to xn, which is the same thing as b. Now choose any point in the subinterval and denote it as x1 star, x2 star, up to xn star. The ith rectangle, okay, the sum of the areas of the rectangle is this sum, though there's a sigma notation. We didn't go over it, but it's just saying keep adding this up. So this is the height times the width, so that gets you the area of that little rectangle. And then you add up all those areas. So this is another formulation where it's delta xi, whereas just the difference of the x's. So if we take a look at this picture, you can see I've got a bunch of rectangles here. And this is just the point where I picked between those two, and that's how you got the upper limit there. You can see it's not always in the center, it's just anywhere you want it to be. Okay, so notice here x sub 0 is right there, x sub n is b. So the area will be a better estimate if both happens, i.e. the number of subdivisions goes to infinity, and the max difference here, right there, this guy, goes to 0, i.e. the size of the intervals gets smaller. So for example, consider, if you just have n go to infinity, this right here can get infinitely many, but unless I make this interval smaller, this area here and here will always be in error. So this overestimation never goes away unless this max xi goes to 0. So the definite interval. If f is a function on the interval a to b, then the definite integral of f from a to b is the integral from a to b of f of x dx is the limit as n approaches infinity, and the max delta xi as goes to 0 of the summation I equals 1 to n of this formula. If f is a continuous function on xi, is a point on the ith interval, and the max delta xi as n goes infinity, the limit exists, we say the f is integrable. Okay, so that's the definition of it. And trust me, this is not very helpful because it's a limit. So what do we have here is the fundamental theorem of calculus. This is what's going to tie it all together for us. So let f be a continuous function on the closed interval, then the definite integral of f exists on the interval, and the integral of a to b of f of x dx equals f of b minus f of a, where f is any function such that the derivative of f, big F prime of x, is small f of x for all x on the AB. Now, I have this here because f of b minus f of a is noted this way. That's the way I was in school. Newer books have it with just a straight line. That's actually a bracket. Some books I saw, it looked it up, it has brackets on each end. Some have brackets and then have x equals a to b, and then some have it this way. So the big question here is, what does the fundamental theorem of calculus do for us? So let's put a box here real quick. Choose blue, make that a little bigger. So while you're thinking about that, so it allows us to calculate the definite integral by taking the difference of an appropriate indefinite integral using the endpoints. In other words, we don't have to use those infinite sums. We don't have to use that summation. This right here is called sigma notation. We don't have to use that. We don't need it. We just take the endpoints of an indefinite integral. So all the stuff we did in chapter 12 and 13, and that's what we use. So the definite integral. So let's take a look at this. Now, we've seen something like this before. Remember when we did the Simpsons rule? We had x cubed, but we did it from 0 to 1. So let's take this same function and go, well, what would this be from 1 to 3? So now we have the integral from 1 to 3 of x cubed. So we integrate that. X to the 4th over 4 evaluated from 3 to 1. So that becomes 3 to the 4th right here. That becomes 3 to the 4th over 4 minus 1 to the 4th over 4. 81 over 4 minus a quarter is 80 over 4, which is 20. So this right here has 20 square units. Exactly. Now, if you're typing this in the calculator, this is the older style. This is the newer style here. So what we're going to do, let me move this over and get the calculator. So we would have x to the 4th divided by 4. So now we'll quit variables, y variables, function y1, and we have 3 minus variables, y variables, y1 of 1. Hit enter, and notice we get exactly 20. Find the area under the curve, the integral of 3 to 5 of x cubed plus 4x plus 1 dx. So we're going to have, this is going to be x to the 4th over 4 plus 2x squared plus x. And we don't need to add c here, because if we add c when we evaluate it from 3 to 5, we're going to end up canceling those c's out. So let's go here to the calculator one more time. So I'll clear this. X to the 4th over 4 plus 2x squared plus x. And I can actually go up here, copy that. And I end up with 170. I would like you to try this one. Okay, you should be back. So let's integrate this. That would be 12x cubed over 3, which would be 4x cubed plus x squared minus x evaluated from 0 to 4. So this is going to be, well, if I plug in 0, that's going to go away. So that'd be 4 cubed plus 4 squared minus 4 minus 4, 0 cubed plus 0 squared minus 0, which is just 0. So 4 to the 4th, 256 plus 16 minus 4. So that would be 256 plus 12, 278. No, not 78. 68. 268. So I'd like you to do that one. And that looks like a U substitution. Hint, hint. Okay, so you should be back. And we will have u is going to equal the higher power one, so 6x squared minus 7x plus 8 because it's to the fourth. Du equals 12x minus 7 dx. And that's exactly what we have, right? So I'm going to integrate this down here. So this would be u to the fourth du, which equals u to the fifth over 5. So this is going to equal 6x squared minus 7x plus 8 to the fifth over 5. So this integral here would equal 6x squared minus 7x plus 8 to the fifth over 5, evaluated from -3 to 4. So that would be 6x squared minus 7x plus 8 Okay, so there I have the top. I just realized I've got to divide that by 5. So that would be -4 -3. So we're going to get -280703053.4. So let's take a look at some of the properties of integrals. So f of x, u of x, v of x are integral functions on AB. So the integral of a to a of f of x dx equals 0 because that's f of a minus f of a. If you have the integral of a to b of k f of x, the k comes out where k is some constant. So just like the other integrals and the derivatives. If you integrate the sum, it's the sum of the integrals. If you integrate the difference, it's the difference of the integrals. If you integrate from a to b, it's the same thing as negative integral b to a. If f is continuous on some interval containing a, b, and c, then integral of a to b equals a to c plus c to b. C does not need to be between a and b. And if you think about it, this is f of b minus f of a. So f of c minus f of a plus f of b minus f of c is the same thing. And that's what this side says. So let's take a look at the idea of area under a curve. If f is a continuous function on AB, f of x is greater than or equal to 0 on AB, then the exact area between y, f of x, and the x-axis from a to b is given by the integral of a to b of f of x dx. So find the area under x squared plus 2 on 0, 2. So the area is going to be integral 0 to 2 of x squared plus 2 dx, which is x cubed over 3 plus 2x evaluated from 0 to 2. And this is going to be what? 2 cubed over 3 plus 2 times 2 minus, that'll be 0. So that would be 8 thirds plus 4. So that's the same thing as 8 thirds plus 12 thirds, which is 20 thirds. So notice in this case it was just as quick to do it by hand as the calculator. So I would like you to find the area under this curve from -2 to 2. So let's start. You should have paused the video and finished. -2 to 2 of 10 minus 4x dx, which is 10x minus 2x squared evaluated from -2 to 2, which equals 10 times 2 minus 2 squared, minus 10 times -2 minus 2 squared, which is 20 minus 8 minus -20, and then this would be also minus 8. So these are going to become positive. So I get 20 plus 20 is 40, and the -8 and the +8 cancels. So try this next one. Okay, you should have finished by now. So this is the integral, -4 to 1 of 5 minus 3x minus x squared dx, which is 5x minus 3/2 x squared minus 1/3 x cubed, evaluated from -4 to 1. So that is going to be 5x minus 3/2 x squared minus 1/3 x cubed. And this would be oy, oy, oy. One -4, and I get 25.8333. And if I wanted to do math, it's the same thing as 155 over 6. Okay, so try this one. So again, I'm going to have a little u substitution going on here. Okay, so you should be back. So we'll let u equal, that's got the square, so it's got to be 4x plus 6x squared du equals 4 plus 12x dx, which is 1 plus 3x dx. So 1/4 du equals 1 plus 3x dx. So the integral of 0 to 1 of 4x plus 6x squared 1 plus 3x dx equals the integral of 0 to 1 of u squared 1/4 du, which is 1/4 times u cubed over 3, and that's going to be evaluated at 0 to 1. So this would be 1/12, and then that would be 4x plus 6x squared to the third, evaluated 0 to 1. So if I put a 1 in, I get 1/12, 4 plus 6, quantity cubed, minus 0. So that's going to be 10 cubed. So I get 1/12 10 cubed, which is 1,000 over 12, which will reduce 250 over 3, which is about equal to 83.3.